Hello everyone. In today's session, we are going to be talking about concavity and the second derivative test. So, as last time we talked about the topics first, what we have covered so far and what we're going to be covering. So, in the last lecture, we talked about open intervals where the functions were increasing and decreasing, and then how a derivative helps us in finding where the function has a maxima or minima by applying the first derivative test. In this lecture, we're going to be talking about intervals where the function is concave upward or concave downward. Then find some points of inflection for the graph of a function. And finally, apply the second derivative test to find the relative extrema of a function. This is another way of finding a relative extrema. So what we have learned is there are two ways. Basically, one is the first derivative test, which helps us to find the maxima minima, and second derivative test also helps us to find the relative extrema of a function. So let's begin with concavity. Now, the intervals where the function increases and decreases gives us the description of the graph. What we're going to do is locate the intervals where the derivative is increasing or decreasing, and this conveys to us where the graph of the function is curving upwards or curving downwards. In other words, is it going like this or is it going like this? So, what is the definition of concavity? If f is a differentiable function on an open interval I, the graph of the function, now this is the graph of the function, is concave upwards on that interval when the first derivative is increasing in that interval. Similarly, the graph of the function is concave downward on the interval when f prime is decreasing in that interval. So that's the formal definition of concavity. We have a theorem that talks about how to test concavity. What this theorem says, that if a function fx has second derivatives on an open interval I, if the second derivative is strictly greater than 0 for every x in an I, then the graph of the function is concave upwards. And if the second derivative is strictly less than 0 for all x in I, the graph of the function is concave downward on I. A very, very important theorem. Notice it's not talking about when the second derivative is 0. It only says when the second derivative is strictly positive or strictly greater than 0, or the second derivative is strictly less than 0. Now, let's look at some of the guidelines which will help us to find the intervals for concavity. So the first thing we do is we locate the x values where the second derivative is 0 or the second derivative does not exist. Then we use these x values to determine the test intervals. Then we finally test the sign of the second derivative in each of these test intervals. And when there are x values at which the function is not continuous, these values should also be used along with the points which are coming from above to form the test intervals. Very similar to your, the increasing, decreasing and your first derivative, but with a catch. Here we are going to look at where the second derivative does not exist or second derivative is 0. And then we're testing the signs of the second derivative at each of the test intervals. Remember, we are talking about concavity. Okay, so let's start with examples. In the first example, we are having a function given by 6 over x squared plus 3 we would like to find the open intervals where the function is concave up or concave down. So I'm using CUs or CDs. Okay, guys, don't confuse with the certificate of deposit, okay? This is concave downward. Nope, no CDs. Okay, not the bank kind of CD I'm talking about here. Okay, so how do we do these? Now if you look at this function, clearly this is continuous and differentiable. And here we have the graph. The graph clearly shows that it is concave downward. Do you see that? This nice little hump and then it comes down. So this is how do we get this? What intervals we'd like to know? Okay, so the first thing according to the steps, we find the second derivative and put that to 0. So the first derivative is negative 12x over x squared plus 3 squared. I'll leave it to you guys to find these derivatives. You can apply the quotient rule. And once again, you apply the quotient rule on the first derivative, you get the second derivative, which gives you 36 times x squared minus 1 divided by x squared plus 3 the whole cube. Now we want to find these test intervals, right? So what you do is you put the second derivative to be 0. So we get 2 points, plus minus 1. Now these two numbers will tell us the test intervals to find the concavity. So what guys we're going to do is we are going to create a little table. So remember, always I do a number line. So just this time I'm going to write minus 1 and 1. Now remember, I'm not making any kind of geometric objects around it because minus 1 and 1, they are coming from second derivative and it is equated to 0. Okay, so I'm just leaving it minus 1 in my head because I want to see what the test intervals are. So the test intervals clearly are from minus infinity to minus 1. The second is from minus 1 to 1 and then 1 to infinity. What we're going to do is we're going to pick up some test values. I'm going to keep the same, notation I've been using, x. So this is say minus 2, 0, 2. These are test values, which I'm going to look at the sign of the second derivative. Sorry, this is second derivative, guys. So the sign of second derivative at negative 2 is positive, and the sign of second derivative at 0 is negative, and the sign of the second derivative at 2 is positive. Now remember, when you are doing, looking at the signs, you have to be careful of what you're inputting. Your second derivative is 36 x squared minus 1 over x squared plus 1 the cube. So that's where the values are going here. So when I put to be 0 here, you can see this is 36 divided by 2 cube, 36, yes, 0. So I think this is not right over here. Okay. Yeah, this value is not right. Give me a second, I'll check it. Oh, my mistake, guys. This should be a 3. I wrote 1 and I was like, that doesn't make sense. Okay, now it's going to make sense because it's going to be 36 divided by 3 cubed. That means 36 divided by 27. And it's going to be a negative because this is 0 minus 1. So negative 36 over 27, which is negative 1.333. Okay, yeah, that makes sense. Okay, so f second derivative 2 is 0.3149. So clearly where it is positive, it is concave up. And where it is concave down, when it is the second derivative at 0 has a negative value and second derivative at 2 has a positive. So how do we write the intervals? Concave up is negative infinity to negative 1 and 1 to infinity, and concave down minus 1 to 1. Just write it in the interval notation. Okay, let's look at another example. It says find all open intervals on which the function polynomial of degree 4x4 minus 4x cubed is concave upwards or concave downwards. Now this is how the graph looks like, guys. We would like to find what are the intervals. Now clearly we can see, like just looking at the graph, oh, this is going up, going down, going up. So we say, okay, what are those intervals? So what we're going to do is, so we see it, from the graph, there are three: concave up, concave down, concave up. So, but we have to do it by the appropriate method. So what you're going to do is we're going to put the second derivative to be 0. First derivative is 4x cubed minus 12x squared. Then you take the derivative of that, gives you the second derivative, 12x squared minus 24x. We have to put that to be 0. So what we get? Either x is 0 or x is 2. So we get two values which will determine the test intervals to find concavity. And remember, no discontinuity because it's a nice little polynomial. Okay. So let's find the intervals. So it's 0 and 2. And as usual, I will draw 0 and 2. Now, I'm not giving any symbol because this is coming from second derivative and we're looking for concavity. So I'm going to have my test values, say -1, 1, and 3. So the second derivative, when evaluated at -1, now remember what's your second derivative. Okay, the second derivative is 12x squared minus 24x. So when it is 1, 12 minus 24 minus 12. Very good, it's correct. Okay, so that means when a second derivative, when evaluated at 1 is a negative number, and when evaluated at -1 it is a positive number, and evaluated at 3 again it's a positive number. So our concave intervals are: concave up is -infinity to 0 and 1 to infinity, and concave down 0 to 1. Notice over here, what did the graph look like? So I'm just going to draw the graph here. So the graph looks like this. You see it's concave up. You see -infinity to 0. Then it goes down and then it goes up like that. So this part which is down is concave down. That's 0, so 1, and then 1 and above. So 0 to 1 it's down, and then 1 and above it goes to, it's a concave up here. Okay. Now let's talk about points of inflection. Now, if a tangent line to the graph exists at such a point where the concavity changes, that's the best way to remember. A point where you see the concavity changes, that point is a point of inflection. There are three types of points of inflection as shown below. So here, nice little curve. This is the tangent line, remember, okay? And here the tangent line is passing through the graph. So concave up, concave down. We can have a graph like this, concave down, concave up. Or you can have a vertical tangent line, concave upwards, concave downwards. The most important part is the concavity of the function changes at the point of inflection. And the graph crosses its tangent line at that point of inflection. Okay? So let's go ahead and give a proper definition and some theorems there. If f is a function which is continuous on an open interval, and let C be a point, if the graph of the function has a tangent line at that point C and f of C, then this point is a point of inflection of the graph of f, when the concavity will change from upward to downward or downward to upward. Now, to find these points of inflection, what you normally do is you take the second derivative, equate it to 0, or where the second derivative is not existing. And a very similar procedure as we just did for finding the relative extreme of the function. The theorem says, if a point C, f of C, is a point of inflection, then the second derivative is either 0 or the second derivative does not exist at that point. Okay, so let's go back to the examples we just did earlier. So remember this function, we talked about the fourth order polynomial x4 minus 4x cubed. We would now like to find the points of inflection and discuss the concavity. We just already discussed the concavity here. So notice from the previous slides, we found that the second derivative is 0 when x is 0 and 2. Now these two numbers give us the concavity. Also look at from the graph. This is the point of inflection because that's where the graph changes from concave up to concave down and then concave down to concave up. Okay. So what are those points? Once again, you have the points 0 and 1. So here, remember 0, we had 1. Here, the second derivative was positive. That means it was concave up, concave down, concave up. So notice what is, there's a change from the concavity upward to downward and then downward to upward. So automatically, this point 0 to 1, guys. And 1 to infinity. So this is the point where it is changing. Let me just check the previous one. Yeah, there's a mistake here too. It's 1. Okay, hold on, guys. Let me see what I'm doing here. Oh, it's 0 and 2. There we go. It was my mistake. I'm sorry. I was right earlier. Okay, good. Didn't realize it. Okay. X equal to, so it is 0 and then it is 2 to infinity. So x equal to 0 and 2. So that point should have been 2, not 1. Okay, that makes the sense. So it's 2. This was right, this was wrong, guys. So 2 is the point. And 0, okay, I made a mistake, guys, here. Let me just correct it. Negative infinity to 0, and this is 2 to infinity and 0 to 2. Sorry. Okay. So, glad I found this mistake. Well, let me correct it here too. So remember, it is 0 and 2. I was saying 0 and 2, and I just made a mistake. My fault. Okay, well, I will make the changes when I put the notes online for you guys. I will make these changes. Okay, let's look at another example. Determine the points of inflection and discuss the concavity of this graph of this function, 2x4 minus 8x plus 3. Now, clearly you can see this graph kind of looks like, a parabola, but it's not a kind of real parabola because parabola is symmetric around the vertex of the graph. So this is a fourth order polynomial given by 2x4 minus 8x plus 3. Once again, function is continuous and differentiable. Let's find the second derivative to be 0. We take the first derivative, 8x cubed minus 8, second derivative, 24x squared. So this is going to be 0 when x is 0. So we only have one point to help in finding the test interval to find concavity. So let's draw that, the table. So the intervals where the functions are concave upward or downwards, it's minus infinity to 0. So just 1 point, remember. So pick up a point minus 1 and a test value 1. And then you look at the derivative of the function at that point. So second derivative at minus 1 is 24 and second derivative 1 is 24. Clearly in both the scenarios it is upward. And we also have seen from the graph goes like this. There's no change in the graph, So that means there is no point of inflection. Okay, so here guys, I would like you to practice finding the open intervals where the function is upward, concave upward or downward, and points of inflection. Thank you.